Good morning, everyone, and welcome to the ARMET's Virtual Student and Early Career Scientists Conference 2020, and thank you for joining us today. Today's session, this is session number 2, which is air quality and modelling, and you have 2 chairs. I'm your first chair for air quality, and my name is Tom Faherty. I'm a PhD psychology student at the University of Birmingham, looking at the impact of air pollution on cognitive function. And I'm going to hand over to Josh just now to introduce himself.
I'm Joshua Hampton, chairing the modelling part of this session. I'm a PhD student at the University of Leeds, studying radar meteorology.
Fantastic. So just so you know the format of the sessions, for the first part, we have 2 speakers, and there's 10 minutes presentation and 5 minutes for Q&A. You won't be able to turn your microphone or video cameras on to ask the questions, so you should do so on the chat function just at the side here. So I'll give you an example. I'm just going to post a question, which is, to myself and to Josh. How do you look so good this morning? Fantastic. And I'd like to introduce our next speaker, who is Jinghua Li. Fantastic.
Hello, Tom.
Sorry, I'm just going to leave you now. Perfect. Same as before, 10 minutes for your presentation, 5 for questions, and if anyone has any questions, please put them in the box. All right, thank you.
Good morning, I'm Jinghua Li. I'm a researcher from the built environment and indoor air quality from the University of Chester. My presentation today is Domestic Energy System and Technology Incubator and Indoor Air Quality of the Built Environment. Next slides. Up to the 1960s, the indoor air quality in the non-industrial area is not on the list of environmental problems. This figure here, this table here shows you the connection between the energy consumption and indoor air quality in buildings from the 1970s to the 1990s, when the public awareness and policymakers has been drawn to the indoor air quality related health and energy issue. 2 points I want to emphasize here. First of all, is most of us spend up to 90% of time indoors. Second is, up to 40% of energy has been consumed in buildings. So that brings us to a question. Can we make a building both energy efficient and healthy for the occupant? Before answering this question, let's have a look at indoor air pollutant and their health effect. Indoor air pollutant refer to indoor chemical, biological, and physical agent that can cause health threat and discomfort. This table here shows you the 7 indoor air pollutants, their indoor sources, and health impacts. As you may see, the indoor sources are mainly coming from appliances, building materials, people, and the activity indoors. Indoor air pollution can be contributed to the health impact, to increase the occurrence of cancers, allergic infections, respiratory infections. If we have a close look at the source of indoor air pollution, so the outdoor air pollutant entering the house through the openings, windows, doors, and cracks, they circulate within the built environment of the house and mixed with the indoor air pollutant. This can vary in different rooms depending on the people and the activities. The 2 effective methods to improve indoor air quality are source control and ventilation, and I'll come back to that later. So based on the introduction, I'd like to tell you a bit more about domestic project, which stands for the Domestic Energy System and Technology Incubator. We aim to develop and build a facility focused on energy efficiency and indoor air quality. There are three components: plant room, sensor unit, and incubator. The plant room will house the instrument and equipment, where the sensor unit will be located within the incubator, providing real-time measurement on indoor air quality and energy consumption. The figure on the bottom right here shows you the design of the incubator. It is a simplified one-bed flat with an open dining area and ensuite bathroom. To make the incubator energy efficient, I have integrated model building solution, passive technologies, and the renewable energy system into the design concept. I've chosen a 20-feet shipping container to be converted into incubator with the off-site construction because it's cheaper, safer, and faster. Silk insulation has been chosen as one of the passive technology, which means you can achieve a thermal comfort without using extra energy for heating and cooling. Windows is another passive technology here, providing us a natural daylight, fresh air, and gain heat on the sunny days in winter. I've also included solar panel. Based on the calculation on the total energy consumption in the incubator, by install a 2.4 kilowatts peak solar panel system, I can make the incubator a nearly zero energy building. Now we have made the incubator energy efficient. Let's move on to the indoor air quality. Overall, it is very challenging to measure the indoor air quality because, first of all, there are limited guardians for the limits of indoor air pollutant. Second, there's no standard index for indoor air quality or a standard strategy to tell you when, how long, and how often the sample should be taken. However, you're able to assess the personal exposure to monitoring to the indoor air quality. We need dynamic measurement and analyze. Thanks to the rapid development of a low-cost sensor, real-time indoor air quality measurement has become available. The bottom two pictures are from my master research project, low-cost sensor for air quality measurement, where I designed and prototyped a sensor uniform, a platform to data log NO2 concentration, temperature, and relative humidity. Here, I'd like to talk about real-time monitoring and indoor air dynamics. As I mentioned before, the two effect measures to improve indoor air quality are source control and ventilation. So it is very important to consider the outdoor conditions, indoor spaces, and activity patterns when we're talking about ventilation strategies, and indoor air qualities. When possible, we prefer to use natural ventilation by opening windows and doors, but sometimes we need to consider the mechanical ventilation. For example, we switch on the cooker hood during cooking in the kitchen. Ventilation strategies may impact the thermal performance of the building, which may require additional energy to fix this. And that brings us back to the question, can an energy-efficient building be healthy to the occupants? And to answer this question, we also need to explore the occupant behavior. This figure here shows you the closed interlink between indoor environment and human factors. It is critical to integrate a human-oriented design into a healthy built environment. Equally importantly is to develop awareness of green concerns and behavior. Also, we need to think about the occupant tolerance to the building and their environment attitudes. A questionnaire option is being shown here. It is often used as post-occupancy evaluation for the indoor air quality by the occupants. To optimize the building performance in a sustainable and cost-effective way with an acceptable indoor air quality can be a huge challenge and opportunity. We have 30 years ahead for the 2050 net zero energy. So, do you think we can achieve it? And why? I think I'm a bit too fast. Right. Here are my reference. Thank you. And any questions? I apologize, a bit too fast.
Absolutely fine. I think we're running a little bit late, so that's perfect. Thank you so much for your presentation. As before, if anyone has any questions, please put in the chat.
Right. It seems
No,
I have a problem to hear from Tom. Maybe can type in the chat box. Okay, I'll read out the. Sorry, Tom, I have to read out myself. Okay, there's a question from Andrew. Could you please share more details on the low-cost sensor you are using? Right, sure. I got chance to go back to the slides. My slides here. Look like already been shared. You like to start sharing? Okay. Right. So, oh, that's not mine. Okay, sorry. I can't share it. Share my screen. Yeah. Okay. Thank you. So I come back to the slides. Where am I? And so here, the bottom two pictures are from my master research project on low-cost sensor. So basically, I'm using Arduino and some sensors. The one of them is NO2 sensors. The other one is a sensor to measure both temperature and relative humidity. And I also have a SD card to store the data so I can process the data later on. And you can change the resolution anywhere between seconds, minutes. Well, you don't want hours, do you? So do you want to know a bit more like specific, or are you happy with the answer? So at the moment, we are thinking of a measure both NO2 and the PM, because in my master research project, I'm trying to integrate both NO2 and the PM sensor, but somehow the Arduino is not powerful. The Arduino Uno is not very powerful to handle both. So later on, if I got more time, I'd like to measure both NO2 and the PM. Any more questions? Thank you. Okay. I'm glad I answered your question. Thanks, Andrew. Right. Any more questions? Maybe I should answer the question and ask myself for the ingredient. Oh, there's one. No. Does it, if there's a window, does it negative anything you for indoor air quality? If there's a window, does it neg anything you do? If human open the window, I think this is pretty much, you have to consider about outdoor conditions. You won't open it if it's like there's like a smoke or a fire or anything, or too many traffic on the road, and or maybe it's too hot on the day and you don't want to open the window and let hot air coming in. So it is you need to balance whether you want to open the window. Is it ruling anything you've done? I mean, the measurement, it probably, because the thing is, I have a weather station to measure the outdoor pollution, the concentration from the outdoor. And then I have my indoor little sensor to measure the indoor concentration. So I can compare both to see what's the X changing rate and what's the influence of the building itself, the building blocks itself. Well, thank you. Okay, there's another one. Do you have any? Have I got time yet, Tom? Okay, cheers. Do you have any ideas on how you would be able to measure PM level as well as? Right. It is it's based on how powerful your the little computer is. Basically, you plug in all the sensors you want to measure. For example, PM, NO2, or some other ones, VOC, whatever you want to measure, any gas or particles you want to measure, you plug them on. And if you want a temperature, humidity, fine, there are plenty of sensors you can choose from online market. You can just plug them on. The thing is, your little computer system needs to be powerful enough to do all the data. So that's need a balance as well, because if you make it too complicated, it either can decrease the resolution, or the quality won't be very high, or it's just too crumbed up. It's tricky to have very accurate readings, if you like. Okay, there's another.
Okay, I'm gonna call it time, unfortunately. So Julia, if you want to contact her personally, she'll hopefully be able to answer that for you. But I'm actually gonna thank you again. So thank you so much for your presentation, Jinghua. And I'm gonna hand over now to Josh, who is chairing the second part of this session. So it's goodbye from me. Thank you so much.
Thank you, Tom. We'll move on to the second part of this session, which is focusing on modelling. Our first speaker is Rachel Sansom. So if you could appear. Cool. And like before, I'll give you a 2-minute warning, and if people can put questions in the chat, we'll come to them at the end.
Perfect. Thanks, Josh. So today I'm going to talk about clouds and why they can be kind of tricky to model. And I'm going to talk about a method called statistical emulation, which can help us kind of understand some of their more complex behaviors. So my supervisors are Dr. Lindsay Lee from Sheffield and Professor Ken Carswell and Dr. Jill Johnson from Leeds. So first of all, I'm just going to run through the motivation for this, and then I'll explain what statistical emulation is, and then I'll just apply it to a kind of simple case study. So clouds are pretty complex, and here in the UK, we're really used to seeing these kind of dull stratocumulus clouds, but even these seemingly quite boring clouds have a lot going on. And especially today, I'm going to think about these stratocumulus over marine environments. So these clouds lay really low in the atmosphere, which means that they don't trap a lot of heat in, but they do reflect a lot of incoming solar radiation. And this means we have a net cooling effect overall. But this cooling effect is pretty uncertain, so there's a lot of research at the moment trying to pin down just exactly how large that effect is. But it's made pretty tricky because these clouds are very sensitive to changes in their environment, and that makes them quite difficult to model. So aerosols are really important here, and these are particles that are suspended in the air, and these are what clouds grow from because they provide a surface for water vapor in the air to condense onto. So we've heard a bit about them already. These can come from natural sources or human sources. So natural could be pollen or dust or sea spray even, sea salt. And then human sources can be kind of soot and particulate matter. So any sudden changes in aerosol concentration can lead to quite sudden changes in these clouds as well. And we can see that from kind of satellite pictures like this, where we have this area of really bright white cloud in the top left corner. And then we've got this more open lacy pattern as well. And then on top of that, we have these really distinct lines running through it. And these are actually from shipping lanes where aerosols have been ejected into the atmosphere from ship stacks. And some of the transitions between these kind of behaviors are very sharp. And this is what makes these clouds kind of difficult to model. So if we just think about the kind of things which might be going on here, first of all, well, specifically in relation to aerosols, if we have aerosol lying above the cloud, we might have the cloud thickening. But if we have aerosol below the cloud, it might tend towards cloud breakup. If we have a cloud raining, the rain might be suppressed and then the cloud will grow. But changes in droplet size affect the cloud size too. So things can get pretty messy. There's a lot of interactions going on here, and they're not independent effects either. So it can be quite difficult to decipher what the kind of overall cloud response is going to be. And we don't always have, well, we won't have all the computing resources that we need to do this, to understand this as one at a time test. And that's where statistical emulation comes in. So the aim of my PhD is to use statistical emulation to try and better understand how these clouds respond to changes in their environment. So if you've heard of machine learning, statistical emulation is a form of machine learning. So if we have a complex model, and this is made up of a huge set of very complicated equations, and for some set of input values that we're interested in, it will give us a set of corresponding output values. But this can get very expensive if I want to know what my model would, how my model would respond for loads and loads of values of X. And this is where we would choose to emulate. So I first of all run a handful of simulations on my complex model just to try and gauge how it, the kind of function it represents. And I use this set of input and output values as training data for my emulator. And I use this with any prior knowledge that I might have about my model. For example, in this case, that it's linear. And I can update that prior knowledge with the information from these training points to give me a posterior distribution for my model. And this creates a mapping from my inputs to my outputs. So it approximates that function, which means that for any new values of X that I'm interested in, I can make a prediction for what my model would output for that value of X. And because this is something called Gaussian process emulation, I get this associated Gaussian error with it, which you can see here. And this is just the uncertainty that I've incurred by using an emulator instead of my complex model. So statistical emulation is a representation of a particular aspect of my model, which provides a surrogate model of the relationship between a set of uncertain inputs and an output of interest. And I can sample this representation of my complex model thousands and thousands of times in literally just a few seconds of computing time. So it's really efficient. And I can get something like this visually called a response surface, which this is for a slightly more complicated case where I've got two inputs now, but I can see how my model output is predicted to change for any combination of those two parameter values. So these dots kind of represent those training points where I know my model's output exactly, and everything else on this surface is a prediction from my emulator. And it has that associated uncertainty with using the emulator instead of the model. So there's a couple of key assumptions that I have to make here about the model's behavior, but I won't go into those here. So then I can apply this to any case that I'm interested in. So here I'm just applying it to this observational campaign that took place off the west coast of California. And that's just because they saw very uniform clouds here. These are the ones that I showed you before. So it's quite a simple case to start from. So these clouds had their cloud base at around 600 meters, and they're about 240 meters thick. And the things I'm interested in here are how does the moisture level and the temperature level above the cloud affect the cloud's thickness? So I want to know, how do these model inputs influence my model's output across a range of values? So if we think back to that response surface, I want to get something like this, where I can see how changing those two affects my cloud thickness. But this isn't real data. We need to fill that in. So we can think about what we might already know from previous research. And that's for wetter, warmer environments, then we tend to have cloud thickening. And for cooler, drier environments, we tend to have cloud thinning. And this green marker, it just shows where my initial simulation sits in that kind of parameter space. And we'd expect that there'll be some threshold there between cloud thinning and thickening. And then I can really easily build an emulator from just a few simulations on my complex model to fill in this whole space to figure out kind of what we might expect from clouds for all these different combinations of inputs. So first of all, I need to decide which simulations to run on my complex model. So I do this using something called a Latin hypercube design. And my complex model is the Monk cloud model. And the output I'm interested in is the liquid water path. So that's an indicator of cloud thickness because it's a measure of the water content in the cloud. So on this chart, each point here is just one simulation on my complex model. And everything about the simulations is exactly the same, except the values of moisture and temperature above the cloud. So you can kind of see from these profiles here how they change. And then each of the pink points are for training my emulator, and I'll run a few extra simulations on my model that I'll use not to train, but to check that my emulator is a good representation of my model. So with just 28 model simulations, I get really good coverage of this input space, and I can validate my emulator too. So when I run this on my model, I can see the output like this, and you see it already that we do seem to have thicker cloud in that top right-hand corner and thinner cloud in the bottom left-hand corner, but there's loads of white space on this graph. But I can emulate that and then really clearly see what that kind of gradient is going to look like. And we can also start to see other information, like for changes in moisture, we actually get a bigger impact on cloud thickness than changes in temperature. So we can get so much more information from this, just from those 28 model simulations. And finally, I just need to validate that this is a good emulator. So I use those 8 simulations that I kept behind, and I just plot my model's output for those points on parameter space against my emulator's predictions for those points. And we can see that it is a really good emulator because it mostly falls within those 95% confidence bounds. And finally, I've got my summary. I'm not sure if I've got any time for this, but takeaway message here is that statistical emulation can be used to visually explore these relationships between model inputs and outputs. And it can go way beyond this kind of 2-dimensional case. Thank you.
We have one question at the moment. It's from Ben. How do you decide how many training points you need to create the emulator?
Yes, so that's a really good question. So I've just showed a 2D case here. People in my group have looked at cases with, I think, nearly 30 different parameters they're varying. And the general rule of thumb is that you need 10 training points for each dimension that you're looking into. So that's why I've got 20 training points here for my 2D case. And then you want, I think we use like 4 or 5 validation points as well per dimension. So it kind of scales as you go up.
I have a question. Well, I don't have any others coming up in the chat. Can you explain a bit about how you quantify the error in your emulation and how much how confident you are that you understand the uncertainty?
Yeah, so this is kind of inherent in the fact that it's Gaussian process emission. So if I just go back, I don't have a plot of it, but I kind of implied it in my thing here. So essentially, because we've run the training points on the complex model itself, then we know that at those points, there is no error incurred from using the emulator instead. But we kind of get this Gaussian shape error between those training points. So for example, where y equals 7 and y equals 15, that's where we know exactly what the model says. But then as we go further away from those training points, the error gets bigger, and then where we're near the training points, then the error is smaller. So in areas of the parameter space where there's kind of a large gap between training points, the error is pretty big, but it's very, or I'm very confident that it's that, like, I'm confident in the emulator's estimation of the error there. Of course, that doesn't account for any error in using the model instead of, say, observations from the real world or something. But it does definitely quantify the error in using the emulator.
Question from Jeremy. So what are some examples of end uses of this modeling?
So that's a good question as well. So at the moment, we kind of want to use it to understand those aerosol cloud interactions a bit better, because it's really hard to untangle those interactions. And that can be used in so there's kind of two scopes here, I guess. There's one for fast adjustments where, for example, you have those ship emissions going up in the atmosphere, and you want to see how those emissions immediately affect the clouds there. But then you've also got longer term ones that you can use this for, such as climate feedbacks. So it's really broad, and that's just within clouds as well. So with climate feedbacks, you could vary, for example, sea surface temperature and winds and that kind of thing, and see how larger kind of like a warming planet is going to affect clouds and their development. But you can also use this. This is not specific to clouds. People have used this in understanding galaxies and volcanoes, and there's loads of things. Anywhere where you want to kind of vary several parameters at in one go and see how that affects the model output, you can use this for.
Brilliant, thank you. We don't have time to get to the last question, I'm afraid. We have to move on to our next speaker. So thank you very much, Rachel.
Perfect. Thank you.
Our next speaker is Michael Lay. So if you're there, would you join us? Thank you.
Yeah, so thank you for the organizers. I'll be talking to you about the Atlantic multidecadal variability today. It's also referred to as the AMV, and my supervisors are John, Laura and Rowan from Reading, and Nick and Doug from the Met Office. So my project is actually about how this anthropogenic aerosols, so man-made aerosol pollution, affects the AMV and the mechanisms. But the first part of my project is just about characterizing the internal AMV drivers in our model that we'll use for experiments. So what is the AMV? The AMV is an observed sort of SST across the whole North Atlantic. If you look in the right, the time series, the black line, just ignore the red and blue, that's the SST time series for the whole North Atlantic. You see that it goes through decades of warm and cool periods marked by the pink and blue shades. And yeah, and it has also a sort of pattern associated with it. It's this horseshoe pattern with the loading in the subpolar region you can see on the left, with a north-south dipole of the red and blue across the whole Atlantic basin. And it's got a period of about 50 to 70 years, although the time series is very short. And why is this important? Because it's been linked to a lot of climate impacts around the world, such as number of Atlantic hurricanes, Sahel and Indian monsoon precipitation, summer climate over Europe and America, and also Greenland ice melt, and well, a lot of other things as well, such as ITCZ position and so on. So what might be driving these changes then? This is quite a complicated picture. So the very leading hypothesis, I guess, is the AMOC. The AMOC is an ocean circulation that's quite unique to the North Atlantic. It's called the Atlantic, well, the whole Atlantic, the Atlantic Meridional Overturning Circulation. And it's unique because it drives northward heat transport across both hemispheres, which is the reason why Britain is so much warmer than places like, say, Newfoundland in Canada, which is at about the same latitude. And it's driven by dense water forming at the very high latitudes, which sinks and causes this overturning circulation to run in the whole basin. And when the AMOC spins up, as you can see at the top left diagram, it drives a lot of heat into the North Atlantic, and that causes a positive phase of the AMB, and that itself provides a negative feedback because a warmer sea surface decreases the surface density, so dampening the deep water formation at the high latitude, and the AMOC weakens. Therefore, you have anomalously less heat transport into the north, and you have the cooler surface, and yeah, and it provides a mechanism for a self-sustaining mode of oscillation. But we don't think this is what happens because another big feature of the North Atlantic is the NAO, the North Atlantic Oscillation, which is atmospheric mode of variability that's characterized by a low pressure cell in the North Atlantic, in the high latitudes, and a high pressure cell in the south. And it's associated with a stronger surface jet, stronger surface westerly across the mid latitudes. This has the potential for cooling across the whole mid latitudes, causing enhanced heat loss and formation of dense water. Yeah, so the NAO can vary from periods of days to decades, and it's the integrated effects that we think might be important for this slow response for the AMOC. And then there's additional uncertainty about whether the AMV can actually force an NAO state, given that a warm AMV, say AMV positive, decreases the north-south temperature gradient across the North Atlantic, and therefore the pressure gradient as well. So giving another possible negative feedback effect. The difficulty in understanding this is, well, we're just not sure about what the relative role of each of these links are. They probably all play a role, but we don't know how much. Yeah, so it's a complicated phenomenon with coupling across many aspects of the climate system, and I haven't mentioned it also probably couples to the cryosphere in the high latitudes, where the sea ice is probably working with density anomalies and so on. Very short observational records, as I presented in time series, we only have about 1.5 wiggle, so not really enough to tell us about whether it's a persistent mode of oscillation. Although climate proxies do suggest that this AMV has been going on for thousands of years. Also, we have model uncertainties. A lot of models simulate some sort of AMV-like behavior, but with very, very different mechanisms. And obviously in the records as well, we have time varying external forcing from greenhouse gases and aerosol. And we think that aerosol probably has a great role to play in this mechanism by either just surface cooling from the European and US emissions during the industrial era that caused sort of horseshoe shaped cooling that's related to the, well, we think might be related to AMV, or it can actually cause a positive phase of the AMV instead by spinning up the AMOC by cooling the surface and creating dense water. That is a really uncertain piece of the puzzle so far that we don't really understand yet. So my work so far has been to characterize the internal, so the pre-industrial condition AMV inherent to the climate system itself in the latest Met-Office model that's used in lots of CMIP6 experiments, the HatGem 3 GC3.1. And the key thing about this model is it's designed so that it can be configured at lots of different resolutions and complexities of processes. So the two resolutions we look at is the medium resolution N216 and the low resolution N96 with a quarter-degree ocean in N216 and a 1-degree ocean in Orca 1. So this is a good way to test how resolution might impact on the mechanism of AMV as well. So yeah, I'll just present some results from this section. So the AMV pattern across the three cases, the observations, the N216 and N96 are largely similar. This is created by linearly regressing the AMV index onto the SST field. Oh dear. Okay, thanks. Yeah, they're largely similar between the models. And we can look at the spatial and temporal evolution of the AMV. And yeah, this is done by lat regression on the SST field. So we can see that 10 years before the AMV, actually it's the Arctic that seems to be leading the warming, suggesting that there is some mechanism with the polar region that's quite important. And you can see the Gulf Stream and the North Atlantic current bringing in a lot of warm water, heating up the subpolar, and the warming then spreads east and south along into the subtropical, forming the tropical arm. In the sea level pressure, we see a very strong NAO-like signal, suggesting that this might be one of the forcing density sources for the spinning up of the AMOC. We can see that the AMOC is anomalously strong before the AMV and then decays away. Yeah, so this is very good suggestion that both atmospheric and oceanic circulations are responsible for the AMV in our model. Similar is for N96. I haven't shown it. There are some key differences, but the broad mechanism is pretty similar. So then I talked about dense water formation. That is a feature that is really not well understood in the observations because, oops, it's going everywhere. Yeah, so we identified two regions, the Labrador Sea and the Jin Sea, which is what we think is happening in the real world. It's pretty consistent with observations. And it shows that, yeah, these are the regions where dense water is forming, where the AMOC is being forced, basically. And we can see that the N96 dashed line is much more stratified in the N216, suggesting that it's much more difficult for, well, it takes a lot bigger density anomalies to force dense deep water formation in N96. Anyway, so the last figure then, I think I've run out of time, but this figure is basically consistent with the loop schematic I showed right at the start. So the red line is the Labrador Sea. It cools. It cools about 2 years to a maximum 2 years before the deepest water is formed in the Labrador Sea. And then 5 years later, you have the AMV peaking. So this is consistent with the AMOC spinning up and taking 5 years to drive heat into the North Atlantic. And then a few years later, the Erminger Sea, and as a proxy for the wider North Atlantic, cools. And this is as a response of just a warmer ocean sea surface, and therefore just passive cooling, while the first peak is to do with probably the NAO, which at the timing is pretty correct with the maximum NAO type SLP anomalies. Yeah, so summary and conclusions, I guess, is that in both models, the broad mechanism is pretty similar, with the NAO being a key source of density to AMOG spinning up, driving the AMV. But there are key differences between the models that I haven't really shown here. But the next step of my projects then is to look at how aerosol will be impacting on these two models. Yeah. So thank you very much for listening. I can take any questions. Okay, so yeah, Tim asks, how significantly could Greenland ice melt be influencing the AMV or its changes over the last century? And do climate models capture this process well? Well, I haven't really considered the Greenland ice melt very much, but literature do suggest that the ice cryosphere coupling is probably happening on a different timescale, more on a centennial timescale, as a much slower response. So the AMV itself isn't one mechanism, one sustained mode of oscillation, and probably superposition of lots of different modes of oscillation. So the Greenland ice melt is probably somewhere in the longer term, which is hard to observe because we only have 150 years of observations. Model-wise, in my model, I haven't shown the results, but the sea ice, not in the Greenland region, but in the Jin Sea and the Barents Sea region, the two big red polar blocks here, it seems to suggest that they are passively responding to the SST rather than actively driving the SST through ice albedo effect, or even actively driving the density through affecting the salinity level. So in our model, it seems like the ice is not too important. It's just passively responding to other variability. But yeah, we need to look further into that. It's unclear. And Nicola asks, have you considered whether the Arctic oscillation may be related to these results? Yes, so in the density analysis that we've done, we see a very, very big signal, especially in N96, of saline Arctic water from north of Svalbard flowing into the subpolar region. That might be an additional source of density on top of the NAO. I'm not sure how that might relate to the Arctic oscillation, because that happens on quite a long time scale as well, so like 70 to 80 years. So I'm not sure, I haven't looked into it. Thank you for the question though. I'll have a look. And question from Max. Going forward to your experiments with aerosol effect on the AMV, will you use both resolutions still? Or do you think the N216 is necessary resolution? Thank you, Max, for the question. And at the moment, we've only had time to start the experiment in N216. It would be nice to look at N96 because I think there are some key differences in the resolution, but I think that N216 probably does a better job at capturing the realistic mechanism because of the more realistic Gulf Stream and the associated impacts. So, but we think also that this model is quite sensitive to aerosol anyway, so it might be better to have a few different cases, but we've only done N216 at the moment, and yeah, that's what we're going with at the moment. Yeah. Yeah.
We'll move on to the final talk in this session, which is from William Doe. If you're able to join us.
Hello.
Brilliant. Thanks very much. Over to you.
Okay. Okay, morning all. So this morning I'm going to give a presentation called The Influence of Anthropogenic Aerosols on the Aleutian Low. This work has recently been submitted to a journal, so I appreciate any comments or feedback that you might have. And this study was conducted along with my supervisor, Amanda Maycock, Marcus Lofstrom, and Chris Smith. So the study was motivated by our incomplete understanding of the Pacific decadal oscillation, which is the leading mode of decadal variability of sea surface temperatures in the North Pacific Ocean. As you can see in the schematic, changes to the PDO, which oscillates between warm and cool phases, have been shown to correlate with hiatus and surge events in global mean surface temperature. And therefore, increasing our understanding of what drives the evolution of this PDO will in turn increase our ability to predict more accurately the near-term decadal climate evolution. So the PDO itself is not a single physical mode of variability, but it represents a combination of processes. And traditionally, it's been thought of as being a purely sort of natural phenomena, but research has suggested that it might be susceptible to external forcing, anthropogenic forcing. And in this study, we consider aerosols as the forcing agent, and we focus on the Aleutian low, which is shown in the schematic, is a process that's widely considered to be the dominant process in sort of governing the evolution of the PDO. So the Aleutian low itself is a semi-permanent low-pressure system located near the Aleutian Island in the Bering Sea, and it's present during Northern Hemisphere winter. And its intensity is represented by this North Pacific Index, which is defined as an area weighted average of sea level pressure over the North Pacific Ocean. And as alluded to in the previous slide, variability in this NPI is considered to be a precursor to PDO variability. So understanding the Aleutian low better will in turn enable us to better understand the PDO. So just to highlight the uncertainty associated with our understanding of the effects of aerosols on the PDO, we can compare two recent studies, one by Smith et al. And one by Udar et al., and both of which occurred in the last few years. So Smith analysed a bunch of transient historical runs forced only with aerosols and focusing on just the period between 1998 and 2012. And he observed similarities between the observational data and the model runs that were only forced with aerosols. And based on this observation, he concluded that the models that he analysed robustly simulate a negative PDO in response to anthropogenic aerosols, implying a potentially important role for anthropogenic activity. However, the Udar paper challenges hypothesis when he analysed a 50-member large ensemble set from one particular model, concluded that the ensemble members that were analysed by Smith lay at one end of the distribution, and that the ensemble mean does not exhibit this negative PDO pattern that Smith had hypothesized. So the approach taken in this study was to firstly analyze climate model outputs from the precipitation driver response model intercomparison project. 11 models were analyzed, each of which performed an array of idealized perturbation experiments. And these experiments included global and regional perturbations of black carbon and sulfate, and in addition to a global perturbation of carbon dioxide. Shown here is the mean distribution of the aerosol burden anomalies across the experiments. So the figure clarifies that the experiments that end with an A or an E, so for example in panels B, D, and E, they represent experiments where burdens only within a specific region were scaled. And the number denotes the magnitude of the scaling. So for example, BC times 10A is an increase in black carbon burden by 10 times in the region of Asia only. And additionally, it's worth noting that the models differ in how they represent the aerosols. Some either prescribe concentration fields and some prescribe emission fields. It's just how the models are set up. And shown here are the responses of the Aleutian low across all experiments and all models. Now, there's a lot of information on this plot, so I'd just like to point out a few key features. Firstly, the left panel shows the response of the models to a global black carbon perturbation, and the left two columns separate. So the two columns in the left panel separate coupled response to a fixed sea surface temperature response. And in both cases, we see a robust weakening of the Aleutian low. And these similarities between the coupled and the fixed sea surface temperature response suggest a small role for ocean feedbacks. And interestingly, when you look at these results in map view, we see that the weakening of the Aleutian low in response to black carbon is associated with this pattern of sea near surface air temperatures, which approximate a negative PDO pattern. And the response to sulfate perturbations is more variable. And however, we see a different response between the coupled runs and the fixed sea surface temperature runs, which in itself suggests a greater role for ocean feedbacks. So the question that we raised from these results was, can we attribute any of the changes in the Aleutian low character to underlying mechanisms? And in order to do this, I used a linearized version of the portable university model of the atmosphere PUMA, which is called LUMA, to solve primitive equations on terrain following signal levels. Now, these equations consisted of prognostic equations for divergence, vorticity, temperature, and surface pressure. And we fed in background states derived from the control runs from the PDR models themselves. We then forced the LUMA model with diabatic heating anomalies associated with the precipitation anomalies and the atmospheric absorption anomalies derived from our PDR experiments, which are shown in the blue and the red panels here. So here we show some results from the LUMA analysis in response to the black carbon diabatic heating anomaly. In the left, the four panels on the left show the divergence, geopotential height, and meridional and zonal wind fields. And this is all showing results at the top of the troposphere, so sigma equals 0.35. And the key features we can see here are an increase in divergence around the Indian Ocean, the equatorial Indian Ocean. Okay, thanks. Which qualitatively, a ridge in geopotential height over Asia, which qualitatively resembles what we saw in the PDR results. And we also see these patterns of meridional wind fields emanating southeast and northeast from over Asia. So these Rossby wave type patterns in meridional winds. And we also see a sort of poleward shift in the zonal winds. So that was a full field. So in order to sort of separate that down into its regional constituents, we were able to detect that the dominant regions contributing to this full field response came from China and Nepal and India. That's just summarizing what I've just said. And so here are the responses to the diabatic anomalies associated with the other experiments, so the BC times 10A, the SOL times 5, and the SOL times 10A. And we can see when we compare them to the responses from the PDR multi-model means, we see that the linear model does not capture the response in the SOL times 5 experiment, which is the top array of panels. Whereas in contrast, the model does a relatively good job in capturing the response over North Pacific in the SOL times 10A, which is the middle row of panels, and in the black carbon times 10 experiment, black carbon times 10A experiment, sorry, the linear model does broadly resemble the PDR multi-model mean over the North Pacific. So one thing to finally note is that the majority of the response over the North Pacific to black carbon 10 and black carbon 10A is due to the aerosol heating effect over India and China, with comparatively smaller contributions from the latent heat of precipitation. So the atmospheric absorption is the dominant source of heat. And so just in conclusion, we've seen that black carbon aerosol perturbations modulate the strength of the Aleutian low through the excitation of anomalous Rossby wave trains originating from India and China. These modulations can induce PDO-like surface temperature patterns in the North Pacific. And we do not see a consistent projection of onto the Aleutian low in response to global or regional sulfate forcing. And our results that I've just shown contrast with those from Smith and Udar, who show a weakening of the Aleutian low in response to these aerosol perturbations. So thanks for listening. If anyone has any questions, I'd be happy to answer, and my email address is on the bottom there for anyone who wants to follow up with any discussion.
Well, we do have time for a couple of quick questions if any pop up in the chat. Okay, Max has a question. So since the black carbon perturbations you showed is 10 times, would you expect a statistically significant effect on the Aleutian low strength of pre-industrial to present day DC changes?
Okay. So the one thing to sort of note is that the black carbon perturbation, the 10 times black carbon perturbation has been scaled up 10 times from present day conditions. So it would be, we would have to, knowing what the jump is from pre-industrial to present day and comparing that, and seeing what magnitude of change that is in comparison to the present day to 10 times. I'd have to know that sort of comparison before deducing whether it would be statistically significant. The one thing to also say is that the black carbon perturbation in the PDMIC experiments was only done by increasing the burden by tenfold, whereas in the sulfate experiments there's a 5-fold increase and a 10-fold increase. So I don't know whether it's linear in terms of statistically, whether, for example, a BC times 5 would be statistically significant, or whether there is some non-linear character to the black carbon that makes it more significant with a linearly larger perturbation. I'm not sure whether that answered the question, but I know that I didn't state in the presentation that these perturbations were from present day conditions, not pre-industrial conditions.
I think we're running a bit close on time. I'm sorry, my laptop's just gone to sleep. I can't check.
So it says we're technically over by 5 minutes, but there's another question from Michael. I don't know whether I've got time to answer that or not.
Yeah, so yeah, we're a little bit over time. The next part of the conference, the kind of social refreshments with the photography competition should have begun. I guess if you want to answer that question, you can stay here and have a quick chat about it. But also for anyone else wanting to head over, just, yeah, we are running a little over time.
Okay.
yeah, otherwise, yeah, okay. Thank you to all our speakers who have joined in with this this session, and hope for everyone else that you enjoy the rest of the conference.
Just to reiterate that, absolutely. Thank you, everyone, again, and also thank you, Josh, for being my co-chair.